Okay, all right. So ideal diode analysis. Let's look at a example today, and we're going to look at an example with multiple diodes. Okay, multiple diodes. So 306. There we go. Multiple diodes. And what the heck? Ideal diode is too simple. Let's do constant voltage mode. That's a lot more fun, right? Uh, okay. All right. So ideal diode and constant voltage. Yes, go ahead. Yes, I moved it. There's some, sorry. I think till tomorrow. Till tomorrow. I was going to announce that, so thank you for bringing it up. There are a couple of questions about some problems in the homework, and so I moved it forward. All right. So what was the first thing? Oh, yeah. Remember, if you're using ideal diode analysis or constant voltage model, then the number of possible combination depends on the number of diodes. Each diode can have on or off states. So the total number of combinations possible is 2 raised to n. So here n is equal to 3. So the number of possible combinations is 8. So when we first begin our analysis, we make assumptions on whether which diodes are on and which are off. So the question here is, analyze using CVD, constant voltage drop model. Okay, constant voltage drop model. Okay, assume that the voltage drop for diode VD is 0.6 volts. Okay, 0.6 volts. As a reminder, yes. What do you mean? The technique? Yeah, technique can be applied to any diode. 1, 2, 3, 4,000, a million. Can be applied to any, yeah. This is CVD, constant voltage drop model. CVD, by the way, in my field, CVD stands for chemical vapor deposition. It's the process that is used to grow lab-grown diamonds. Chemical vapor deposition, semiconductor process. Pass methane gas, something that contains carbon in a vacuum environment. Set the vacuum chamber pressure and temperature to the right conditions with the diamond seated on your sample, and then it decomposes into carbon. If you did the process correctly, the carbon atoms link up and deposit as diamond on your sample. That's CVD. Anyway, coming back from the segue, let's assume that all 3 diodes are on. Okay. So first, make an assumption. Let's assume all 3 are on. Okay. Now, as a reminder, ideal diode analysis, if we assume that the diodes are on, then they're replaced with a short circuit, and we check for the forward current. In reverse bias, if we assume that a diode is off, in reverse bias, we check for the voltage. It should be negative. In a constant voltage drop model, CVD model, the reverse bias is exactly the same as the ideal diode model. Meaning if we assume a diode to be off, we check for the diode voltage. If we assume that the diodes are on, as we are doing in this case, then they're replaced by a constant voltage source of 0.6 volts. The voltage source will have a polarity of plus at the anode and minus at the cathode. And so if we assume that all 3 of them are on, the circuit looks like this. Okay, circuit looks like this. And then we perform our analysis. And at the end of our analysis, what do we need to find? We need to find the forward diode current. Okay, if all three of them are on, we need to check and verify ID, diode currents, for all three diodes, right? We are assuming all three of them are on. So we need to verify it for all three diodes. Okay. Okay. So let's begin. All of semiconductor devices, the circuit analysis techniques are still the same ones that we learned previously, right? Circuits 1, 2, and 3, we learned about resistive circuit analysis, Ohm's law, KVL, KCL. All of that is still going to be used. Okay, circuit analysis techniques, they are still the same. Only the models that we use will change. So in this case, I have diode D1, diode D2, diode D3. And if you notice, the voltage source's polarity, where did it go? The polarity of the voltage sources is exactly as the ones that we saw in the original circuit diagram. Okay, so everything is replaced with a constant voltage source of 0.6 volts. Now let's apply our techniques or analysis techniques and calculate for the diode currents, ID1, ID2, and ID3. Okay, so ID1, ID2, and ID3. Now, the directions for those currents will come from top. Okay, because this is plus 10 volts and because I have minus 20 and minus 10 here, I'm going to assume that the currents are flowing in these directions, plus to minus. All right. What do we see up front? We have nodes A, B, C, D, or A, B, C. I can estimate that VC is minus 6 volts, right? VC is minus 6 volts. VB is going back up again. So here, look at the far right. At the far right, I have this, which is 0 volts, right? It's going to hit the ground, so it's 0 volts. Then I have a voltage source. That voltage source is 0.6. What is the property of a voltage source? The property of a voltage source is that it supplies its rated voltage between its terminals. So if it's plus and minus this way, and the right end, the positive end of the source is at 0, that means the negative end has to be below 0, so minus 6 volts. VB, if VC is minus 6, VB is 0.6 above VC. So we get 0.6 minus 0.6. And so that becomes 0 volts. So then take a look at the circuit. Tell me what is VA. So one answer is minus 0.6. What do y'all think? Plus 0.6? Yeah, it is minus 0.6. Okay. So we have the 3 node voltages. Now apply the voltages, node voltages to the circuit and calculate the currents. Okay, let's look at the three currents. ID1, ID2, ID3. If we have a resistor anywhere in the pathway, it makes our job easier. We can simply apply Ohm's law to those resistors and we can calculate the current. But there is no resistor in that pathway except for R2 here. So we could possibly calculate IR1 or ID1 directly. Okay, sorry, IR2 right here. ID1 is going through here. So you could possibly calculate that directly. The other current we can calculate is the current flowing through R1, IR1. So those are the two currents we can calculate. We can also calculate IR3. Okay, so let's go ahead and do that and see how they will aid us in finding ID1, ID2, and ID3. Okay. So the reason I'm speaking this out loud is just to show you that the approach for every circuit is going to be different. The approach for this circuit is, what is my goal? My goal is to find the diode currents, ID1, ID2, ID3. Now, I cannot directly apply Ohm's law to the diode, but I can apply it to a resistor. The only resistor in pathway of the diode is this one. Okay, and that's what I'm going to do. So I'm going to apply Ohm's law over there and find IR2 first. So if I find IR2, I can write the equation. It's VA minus of minus 20 divided by R2. And VA is minus 0.6 plus 20 divided by R2, which is 10,000. Okay. Calculators out. Solve it as we go along. Tell me what values you find. 1 milliamps. So 0.6 or 20 minus 0.6, 19.4, 19.4 divided by 10,000, 1.94 divided by 1,000, so 1.94 milliamps, right? Not 1.94 milliamps. All right, the next one I would like to find is IR1. IR1 is rather straightforward. Simply 10 volts minus B, which is 0, divided by 10,000. So 1 milliamp. And then IR3 IR3 is between node C and minus 10 volts. So VC minus of minus 10 divided by R3. And that gives me minus 0.6 plus 10 divided by 10,000. So 9.4 divided by 1,000 divided by 10,000. So 0.94 milliamps. Okay, we have three currents. So from these three, how can we go about finding the diode currents? What techniques come to mind? KVL, yes, but we have currents. KCL. So all of circuit analysis is just based on three, right? You've heard me state this before, perhaps. Ohm's law, KVL, KCL. Everything else is derived from these three techniques. If we wish to find voltage, think of KVL first. If we want to find current, think of KCL. And for everything else, of course, there's Ohm's law. So how would you go about finding the diode currents? ID1. Exactly. How about ID2? Okay, IR1 minus IR2. How about ID3? IR3 minus ID2. What do you all think? Let me write it down. All right, so, all right, somebody on Zoom, please send a test message. So now let's find ID1. ID1 is going to be the same as IR2. And so IR2 is 1.94. What is our original assumption for this diode? It's on. And the diode current is greater than 0. So we can say our assumption could be correct. We got one green. All right, let's see ID2. ID2, what did we say ID2 was? So what is this answer? Ooh. This one turns out to be negative. So if it's negative, that means ID2 is less than 0. So assumption is not valid. Just take a few seconds to think about it. Let me know if you have any questions. Because we assume the diode is positive. So we assume the diode is on. Yes. D1 on, D2 on, D3 on. So if the diodes are on, then the currents must be positive. So we made an assumption at the very top. And when we find our answers, we need to check them against our assumptions. So if it's not matching up with our assumption, that means our assumption is incorrect. So at this point, if I was solving a circuit, I may or may not proceed. But since we are trying to solve this for the benefit of the students, then let's go ahead and calculate ID3. And ID3 would be IR3 minus ID2. So this will be 0.94 minus of minus 0.94. So the sum current turns out to be 1.86 milliamps. ID2 is greater than 0. That means my assumption for ID3 could be valid. Okay, it could be valid. But not necessary. Okay, think over this. Let me know if you have any questions before I talk about it. Any questions from anyone? Yes. It's there in the lab notebook. You can export it as an image. You can export it as a PDF. You can simply just print it and create a PDF. Okay, so what does it mean for assumption? Well, the question was kind of, well, question was vague. one of the diodes is incorrect. So does it mean all three diodes are incorrect or just one? Good answer. Yes, all of them. So just because 2 out of the 3 had a green tick, meaning 2 of the 3 assumptions proved correct, does not mean our entire set of assumptions is correct. Okay. It could be possible that D1 is also off and not on. It is possible. Okay. But if I am trying to make another assumption, now there are 8 of them, right? There are 8 possible states. I don't want to have to do this analysis 8 times, right? So my next logical starting place or next logical assumption would be that D1 is on, D3 is on, and then D2 is off. Okay. It could be possible that even that assumption turns out to be incorrect, but let's go ahead and make that assumption anyway, and then we'll proceed. Okay. So now we check and verify, and D1 was correct. D2 was incorrect. D3 was correct. Okay. So our entire assumption is invalid. All right. So now, second assumption, I'm going to assume D1 on, D2 off, and D3 on. Okay. Remember, there are 7 other possible states. So what can we do now? We can find the currents again by applying Ohm's law to the resistance, right? But because we are assuming that D2 is off, we need to check for the diode voltage. If it is indeed off, then the diode voltage VD2 must be negative. There is no other way for it to be off. Okay, so it must be negative. Does everybody understand? So we are assuming that D1 is on, D2 is off, and D3 is on. So D1 and D3, the currents must be positive, but for D3, the voltage must be negative. Current obviously would be 0. We can see that there's a break in the circuit, so current flowing to the diode would automatically be 0. But the diode voltage VD, anode positive, cathode negative, VD2 must be less than 0. Otherwise, our assumption cannot be verified. So if we want to find the voltage, the easiest thing we can do is apply KVL. Right? We can apply KVL around the loops. We have 2 loops, one on the left, one on the right. Okay. So go ahead and apply KVL. What do you see? How many voltages do you count? Starting from the top, we have 10 volts at the top. Then we have IR1, sorry, not IR1, VR1, voltage across R1. Then we have the diode voltage drop. So I'm going to the left right now. Okay, I'm going to the left. Then I have the diode voltage. Then I have the voltage drop across R2. And then finally, the 20-volt source at the end. So 1, 2, 3, 4, 5. 5 voltage drops, 5 voltages. Okay. So since we need to find voltages, let's apply KVL. If you apply KVL to the left loop, what do I obtain? I obtain 10. And you can apply KVL in any manner that you're accustomed to. Right? 10 minus IR1 times R1 minus 0.6 minus IR2 times R2 and then minus of minus 20 is equal to 0. Okay. Let's substitute the values in there. And what do we get? 10 minus IR1 times 10,000 minus 0.6 minus IR2 times 10,000 plus 20 is equal to 0. But now IR1 and IR2 are the same. No difference, right? There's only one loop because of the diode in the middle that is open. There's only one loop on the left, one loop on the right. And we can say IR1 is equal to IR2. It's the same. And we can solve for that current because everything else is known in the circuit. So IR1 is equal to, take everything else on the other side, 29.4 divided by 20,000. And now obtain a current of 1.47 milliamps. And luckily for us, our diode current ID1 is equal to IR1, which is 1.47 milliamps, which is greater than 0. So our assumption of the diode being on is verified. Okay. All right, let's calculate IR3. IR3 in the same manner is going to give us ID3. And this is rather straightforward because there's only two voltages. IR3 has 0.6 at one end or minus 0.6 at one end and 10 at the other. And so this is minus 0.6 minus of minus 10 divided by 10,000. This becomes 0.94 milliamps. Okay, 0.94 milliamps. Now apply KVL to the right loop. And on the right, I have plus 10 minus 10,000 R1 of IR1 minus VD2 minus of minus 0.6 equal to 0. So, yeah, it doesn't go to the left. So here, because of the break in the middle. I should put a green tick mark here also, 0.94. Okay. So now VD2 is 10 minus 10,000. And this would be, what do we have? IR1 is, excuse me, 1.47 milliamps. So 1.47 times 10 raised to minus 3.0001, no, 0.0147 plus 0.6 is equal to 0, actually not 0. And therefore, my VD2 has a value of, anyone? 3.9 or 2.9? You just did the calculation. Anyone? 4.1. Negative 4.1, which is in alignment with our original assumption. Since we assumed diode D2 must be off, then the voltage across diode D2 must be negative. Otherwise, it would not be off. And so, minus 4.1. So all three diodes were verified, and we obtained matching results. Let's see, 0.4. Okay. All right, let's take a pause while you compare those two results. Look at the values for the three diode currents from the first one to the next. What do you see? Anyone? Are the values the same? The values are different, even though assumptions. And that is one indicator of why our assumptions could be different, right? Even if we assume diode D1 on in the first one and it's verified, it does not mean that in our correct assumption, diode D1 could be on. So the values could be anything. I mean, the states could be anything, the values could be anything. All right. All right, the Q points. So the question originally was, find the Q points in the three diodes by assuming ideal diode analysis. So the three Q points for D1, ID1Q is 1.47 milliamps and 0 volts. For D2, it is 0 milliamps and minus 4.1 volt. And D3 is 0.94 milliamps and 0 volts. Oh, sorry, not 0. I keep forgetting this is not ideal diode analysis. It's 0.6. 0.6 volts. Okay, 0.6 volts. All right, questions. If this was, the question being asked is, would it be easier if this was ideal diode model? A little bit, like yes and no, in the sense that the only difference would be that instead of 0.6, there would be a 0 in there. That would be the only difference. So you'd have one less. So if you write the same equations, the same procedure, everything, except instead of 0.6, it would just be 0. So one less term to calculate. But ideal diodes are great if I just want to analyze a circuit and see what is exactly going on. So I just put on, off, on, off, on, off. It makes it easier to just analyze, which is a technique I use to explain rectifier circuits. Well, what do you mean by results? So the question being asked is, would we obtain the same overall result? The answer is yes. Yeah. Yeah. And as you pointed out, the numbers would change. The numbers would be different because instead of 0.6, it's 0 volts. But the overall result, meaning the diode D1 is on, D2 is off, and D3 is on, we would still obtain that overall same result, which I usually point out that students should try at least 2 different assumptions. Try at least 2 or more assumptions and to solve this circuit. Meaning assume that diode D1 is off, D3 is off, and any other combination you want. Okay, just as practice. Also try ideal diode model. Okay, and you should be able to obtain the exact same results. Okay. All right. Who has lab on Wednesday? Anyone? Nobody? Okay. Yes. So the question being asked is, in the ideal diode model, does it become a short based on the bias? Um, Answer again is yes or no, because it's an assumption. We can assume whatever we want. But no, it's replaced with a wire. That's a different question. So the question would be, what do we replace the what do we replace the diode with? We replace it with a wire. Yeah. The assumptions are based on logic, meaning I could assume whatever I want, but logic dictates, or the rules of the circuit dictate, that if there is a positive, if the anode is connected towards not directly, but towards a more positively charged voltage source or positively charged position in the circuit, or the cathode is connected towards a negatively charged, then logic dictates that more often than not, it would be on. And so it's a random assumption, but that assumption is made by us. It's based on logic. Okay. All right. Want to get into rectifier circuits. And then the lab for this week is Zener diodes. So let me just do a quick overview of rectifier circuits, and then we'll end class for today. All right, rectifier circuits are so called because they change or rectify the circuit from AC to DC, right? Almost every electronic device that we use in everyday life all runs on DC, okay? However, power is generated, electrical power is generated and transmitted over long distances in the form of AC. So you've seen those long distance transmission lines running overhead through the mountains and all through the city, or in, wherever near your home residences or anywhere. All of that transmission is in AC. Power is generated in AC. Transmission is also in AC. Everything that we use is in DC, so we need a way to convert AC to DC. Okay. With the proliferation of solar cells or solar panels in the last few decades, what kind of power generation is solar? That's in DC, semiconductor device, it's a DC current. And so for those applications, now there's a proliferation of inverters. Inverters is not something that we actually look at in these classes or in the semiconductor class, but inverters is the exact opposite of a DC. An inverter converts DC into AC. So when they were first coming up with the names, they said, okay, AC to DC is a rectification. We are rectifying it back to DC. And so they named these circuits as rectifiers. And for DC to AC conversion, they say we are inverting the process, or it's an inversion. And so we'll call it inverters. So inverters are now very common because California has a law. Every new home construction must have solar panels on top, and all solar panels generate electricity in DC. If you want to feed it back into the grid, or if you want to use it as part of your home, then you need a way to convert that DC into AC. And so you have inverters mounted on the side of every home. All right, so rectifiers convert AC to DC. The most common way to do it, or the most easiest way to do it, is to use diodes. Diode is a one-way device because AC flows from both positive and negative half cycles. You connect a diode, you take your AC signals, feed it into a diode. It only conducts in one direction. That means the other direction is blocked. Okay, and so it's automatically converted into DC. The conversion, the first step after the diode conversion is not a true DC, meaning it's not a flat line. It's known as a pulsating DC. So the output of a diode rectifier is known as a pulsating DC because it still has a variation. So it's known as pulsating DC. And then we add filtering options in there to actually remove that pulsating DC and make it into a approximately flat line. Okay, so there are many other components that go into building a power supply, but the first one is a diode at the front end. Okay, diode at the front end. All right, we'll end class here today, and we'll pick up here again on Monday. Quiz on Monday will be based on the topics we covered this week. I'm thinking mostly just ideal diode analysis or constant voltage model, constant voltage drop model. So either ideal diode or CVD. Okay. So I'm letting you know right now. On the quiz, it'll be either ideal diode or CVD model. Yes. No, I won't ask that. So you said you want the quiz to have an iterative problem? Oh, how you would do it. Okay. All right. Okay. It's so specific problem on the homework, or yeah, someone sent me an email about it. I think I responded saying that their voltage was correct, but the current kept giving them problems. Did anyone else have the same issue? Okay. So so if everyone is having the issues, then it's probably some error in the system. So I'm going to go ahead and report it. But when students are doing it, is there a report problem or report issue button in there? So see if there's a button, then you report that at your end. The reason being, if more people submit it, then they are likely to look into it very, very quickly. But I'm going to submit it too. So I'll submit a ticket and I'll just let them know that there's an issue with this. And then if there's any points deducted, then I will go ahead and change it. So wait, you're saying that you were able to solve it, so there's not an error? All right, I'll go ahead and try it later tonight or tomorrow, and I'll take a look at it. So it seems that it is possible to solve it. Okay. So thank you for letting me know before I reported the issue. I mean, I was gonna simulate it at my end anyway, because I remember solving it like last year, and I don't think I had any issues with this particular problem. So yeah. So you calculated diode voltage first and then plugged it into and just plugged. Yeah, okay, yeah. How many steps did it take? Yeah. Okay. Was it CVD model? Was it ideal model? CVD model would require, yeah, 0.6. Yeah. But if picoamps, then it's kind of like, yeah, it's not enough to turn it on. Okay. All right. Thank you.